Hello everyone, welcome back to another one-dimensional Riemann integral question. An interesting question that appeared in some preliminary exams in fact. So if you haven't yet, also please consider subscribing to my channel. That's the best way you can support me and make sure that such material keeps coming. Let's go to the question. Suppose f defined on the unit interval is Riemann integrable and that this limit of f at 1 exists, which by mean we also mean it's a finite value. Prove that this limit equals a. Don't miss this n in the beginning of the integral. So, to start solving this, I want to make the following observation, okay? Changing the value, so changing f of 1 to any other value will not affect any of the integrals involved. So, without loss of generality, suppose f of 1 is actually equal to a. In other words, excuse me, f is continuous at x equal 1. So that comes for free. The second observation is that since f is integrable, it is bounded, and let's give this a name. So there exists some m such that for every x from my interval 0, 1, f of x in absolute value is no bigger than m. So that's one thing we know about f. And its set of discontinuities, the point x where the function is discontinuous, is a null set, which you don't need any Lebesgue measure to define. It's just any set you can cover by union of intervals whose length add up to less than an arbitrary epsilon. So we know from the Lebesgue-Riemann theorem that a function is integrable if and only if it is bounded and its set of discontinuities is a null set. Therefore, we can apply that. This is the claim I just made is a consequence of that theorem. Now, taking the other direction of that theorem, we conclude that thus for every n, xn fx has at most a null set of discontinuities. So actually it's a nice exercise that this can reduce the discontinuity at x equals 0, but other than at x equals 0, x and fx will be discontinuous if and only if fx is discontinuous. So and obviously also we have the bound that xn f of x is also always less than or equal to m. So for every n, xn fx is in fact integrable. So that was necessary because just to write down the integral that we want to prove something about, you have to make sure that the thing you write down is actually well defined. You have to answer the question, why can I write integral from 0 to 1 xn fx dx in the first place? And this pain that we took here was just to confirm that actually, yes, you can write down the integral of xn fx. Now that we have that in hand, I get to proving the claimed limit. So it suffices also to show that these quantities, which I call yn, so n plus 1, 0 to 1, xn fx dx, converge to a. This yns are different from the values we wanted only by replacing n with n plus 1. So in other words, if you multiply this quantity by n over n plus 1, you get the integral we wanted. And this thing converges to 1, so it won't ruin anything. That's why I can, for free, actually change the n that we had to n plus 1 here. Now, the reason I want to do this one is for the following fact that we know a, it follows from an easy computation that if you integrate n plus 1 times 0 to 1 xn a dx, then you recover a. So for every n natural number, we have this equality. It doesn't happen in the limit even. It's always true. Just take antiderivative, and that's the reason I actually wanted n plus 1 here, and plug in 0 and 1, you're done. So since I want to show that yn converges to a, I'm interested in looking at this difference. So this will be n plus 1 integral from 0 to 1 xn fx. This is what gave me the yns. Now, because of linearity, I can subtract xn a and then put dx there. And the absolute value is of course here, and we need parentheses. So this one will be less than or equal to n plus 1 integral xn absolute value fx minus a dx from 0 to 1. Now, we want to show, of course, this thing converges to 0, but why is it expected? Here are the moral reasons why this is going to be the case. So, number one is that the fact A that I'm going to use is that near x equal 1, we have small values for f of x minus a, because this is a is just f of 1, and we have continuity at x equal to 1. And to deal with the other remaining part, away from 0, so away from 1, that means away from 1, if you keep a safe distance from 1, then xn are really small. Okay? So this is not proof. This part is like my thought bubble, and that will guide whatever comes next. So focus from now on beating this integral, making sure that it is tiny. So, given if someone gives us an epsilon positive, find delta positive such that the a part, so fx minus a, is less than epsilon for every x, which is pretty close to 1. So that is less than delta. And because, remember, we only are interested in the left side of 1. So this is true, such epsilon delta, such delta positive exists because f is continuous at 1. So that's one thing. Then integral from 1 minus delta to 1, so everything close to 1, and n plus 1 times xn f of x minus a dx will be less than n1 plus 1 epsilon for the absolute value that we have there from 0 to 1 xn dx. And I here also replaced 1 minus delta by 0, but it only increases the integral because I'm integrating a positive function. Therefore, but that quantity is exactly equal to epsilon. So I showed that the integral I wanted from 1 minus delta to 1 part of it is less than epsilon. Now we need to deal with the rest of the integral. On the other hand, n plus 1 integral 1 minus delta to 1 xn. So we are dealing now with the other part. So 0 to 1 minus delta fx minus a dx is less than. So here I want to put the maximum possible for the absolute value in the inside because I have no better upper bound. And then I have n plus 1, then integral from 0 to 1 minus delta. Here I don't touch the range where I integrate because I cannot afford to. But this, if you compute, again, the antiderivative is easy to compute. This will be 1 minus delta to power n. So notice that in the previous estimate, I had no restriction on n. So this is true for every natural number. So I make this integral small even before I let n go to infinity. For the new one that I have, this is the first time I will need to take a limit. So because 1 minus delta is less than 1 and positive, so if we had a larger delta, we can for free make it smaller. So because this is between 0 and 1, there exists some n in natural numbers such that for every n bigger than n or equal to, let's say, 1 minus delta to power n is times the bounds that we had, n plus absolute value delta is less than epsilon. Now if we combine the two estimates we have found, we see that for every n that is bigger than this n that we have found, yn minus a, which was n plus 1, which was less than or equal to n plus 1 integral from 0 to 1 of xn f of x minus a dx is less than 2 epsilon. Epsilon coming from integrating from 0 to 1 minus delta, and then another epsilon from integrating from 1 minus delta to 1. And that's it. So for every epsilon, we found an n in natural numbers such that from that point on, yn minus a becomes less than 2 epsilon. And this is exactly saying that limit of yn equals a, as n goes to infinity. Thanks a lot for your attention today, and hope to see you in a near future video. If you have any questions, please put in the comments, and don't forget to subscribe.